Okay, and we are live. So, I'm going to implement a vector quantized variational autoencoder from scratch. This is like it's take two. I want to do it from scratch to solidify all the other commands, data loading, training, etc. It's good to repeat. It's what worked for me previously when I was coding game engines. I used to implement it from scratch every time, so I'm not sure if I can finish this because some areas are still blurry for me, but the most important takeaway that I got, and it was a misconception of mine, is that normal autoencoders and variational autoencoders, they work like in the encoder's last layer, you flatten your output into a single dimensional vector. And previously I tried to quantize that, which yields that basically you downsample a frame or an image and you try to fit that whole frame into this codebook in latent space, which is just dumb because, for example, if you have a video and a large training set, you cannot create a single token from an entire frame. So what actually the VQVAE does is that you keep that downsampled frame, for example 8 by 8, and you project each of the cells to the latent space. So in this case 64 latent vectors will be present, and you quantize those 64 latent vectors. So each frame is in this case split into 64 latent vectors, and those latent vectors got placed into the codebook. So let's do this. Import some stuff. Pick a kernel. I think it's here. I'm not sure if it's here. Matplotlib we don't need until later. We definitely need torch.nn as nn and import torch.nn.functional as f just in case. We'll need autocasting. I want to do autocasting, and we need the grad scaler. I think it was moved to torch.autocast. That's good. And which library exposes the grad scaler? Torch.amp.grad scaler. Import grad scaler. All right, that's our import section. Load data. I have my own data set ready on Hugging Face. That's going to be the faces 128. It downloads the global cache. That's desirable. We might not even need any other more parameters here. So that's the DS. And We need a train dataset, that's DS train. Test dataset, DS test. Let's instead shorten the code, and I will just do it like this. The batch size is needed, shuffle in memory, but shuffle is true for train, false for the test. Our batch size is a constant. $64 for now. Let's pin the memory for faster copies. Line the code. And we need some transformations, so transform function for an example image equals, and now I will call this data TF, let's say T, which I did not import here. Let's fix that. Import torch vision dot transforms as T. Compose a pipeline, but it's only going to be to tensor. So this is, we call data TF on E for all E in X image, and we return X because our data set has an image column only. We have the two data loaders here, and let's return train as train, that's the train loader, test loader as the test. Now I'm going to return the train dataset as well, but the image column, so we can directly address them and pull images when we want to try some stuff on single examples. Don't forget to line your code horizontally as well, it gives it a nice look. And I'm just going to call it data, because it has data loaders and data set as well. We load our data. Does not accept it because there is no image column. You say because. First I need to pick train and test. Oh, good. Let's define an encoder block for us with input channels, output channels. Yeah, we return an array. It's going to be a convolutional network, no transformers here yet. Later I will replace kernel size stays 3, stride 2, padding 1, so we downsample our image. Now let's use relu in place true. Let's well, I'm going to put dropout here. It doesn't hurt. dropout in place true, dropout, and this time I'm going to add group normalization, and since I know that the output channels will be a multiple of at least 32, you can say I could parameterize but keep it at 16. So groups, out channels, the rest stays the same. Now we have a class for our encoder. And we have a channels list of ints. And we need a D for our latent dimension, latent space. That's the number of dimensions in latent space. So now the channels, and I have to define the input size here as well, I believe, because let's add another code block here. This will be a utility function. And we need to assert that and we need numpy as well, or numpy, whatever you want to call it. We need to assert that length channels plus 2 is smaller than np.log2 in size. Now the log2 of in size, and assuming in size is a multiple of 2, well, in this case it's gonna be fixed 128, and for that you can divide it by 2 7 times to arrive at 1, because 8 is 256, 9 and yeah, the 10th power of 2 is 1024, so that's 7, but we want to downsample it. I think 8 by 8, not any lower, so the latent grid should be not less than 8 by 8. So the log2, okay, I need a new code block here. The log2 of 128 is 7. that's going to be a size of 2. So 6 times u divide, that's going to be 4. 5 times we can divide, that's going to be the 8 by 8 image. This means this is still allowed, because if this is 5, 7, it can be, so that looks all right. And I want to receive the size of the resulting image if I divide it by that many times. So that's going to be what's it gonna be, 2. So I'm dividing in size by np.pov 2 on len channels. So 2 on 5 is the maximum allowed, so that's 32. And if in size, so 2 on the 5th, is 32, and we divide 128 by 32, that's gonna be 4. So actually I cannot allow the LAN channels to be 5 if I want to keep at least 8 by 8 images. Because that's then 128 np.pov 2 on 5, that's too small. So in this case it has to be small, come on, it has to be smaller than 7, so maximum 6. So this is 4. At tops 4 downsampler layers. I could call this downsample, but let's call it ang block. And for C in channels, for E in ang block, the in channel, should we have to zip this, because we are taking out pairs of them. So channels will be like this. So 3 RGB channels, then 64, 128, and for example 256, and we downsampled it to 8 by 8. So we take out pairs of these, we zip it, that's gonna be synths out. It's channels in, channels out, and we have channels in, channels out, a dropout. Keep it 0 for now. Groups, I'm just gonna keep it at the default, definitely. So we have this E, which is the layer. So I take the layer here. Just indent it a little bit, so it looks nice. Yep. Now in the end, with this configuration, we will have 256 channels and 8 by 8. Now this one could actually be the latent dim, or we can add another layer to map that 256 into our desired D. So the in channels -1, the out channels is the D. Kernel size 3, stride 1, padding 1. It's going to keep the size, the padding 1. And so it's going to look like the 8 by 8 in the end. We need a forward function, and we are just going to call net x. This here with our utility function, I'm not sure if we need this value, but at least we calculated it for it might help later. Let's call ensure sizing with channels and in size. Also, a nice little trick I just learned not long ago, and you have to ensure that the size is a power of 2. Well, first check that the in size is greater than 0, and if you end it like this, this has to be 0, because every number that is a power of 2 has only one bit set, the rest are zeros. If you subtract 1, then all the other bits will turn 1s. And if you end them, it has to be 0. But this is only true if the number is greater than 0. So let's take our decoder. And we use conv transpose 2D here. With a kernel size of 4, stride 2, padding 1, group norm okay, reload okay, drop out same way. And the channels will be provided in a reversed order. That stays the same. This time we need a convolution here, and we convert from D to channels 0. And in the last layer we need a sigmoid, because we are reconstructing an image with values between 0 and 1. So we would need a decoder block with the same way. Actually, I spelled this wrong, because we want it like this. So this will omit the last layer in the channels, and we can do manual last layer here. It's gonna be, so if we provide it opposite way, just need channels -2, channels -1, it upscales it. Groups, do we need a, I'm not sure if we even really need that normalization here. It's not a relu, it's a sigmoid, no dropout. Yep. So that's our decoder. Now we need the most important bit, also the most complex, is the vector quantizer. I'm just gonna copy, it's easier. So we have our D and our K, which is our codebook size. So we have our codebook. Also need to store K and the D. And this is an embedding, a matrix. So this is K to D. So K vectors of the dimension D. We have to have a beta parameter for training. By default, stick to a suggested 0.25 and save it. So now I'm not sure if I can write this from head, but let's try. We could call our codebook C something. So this actually takes ZE, which is a latent vector, actually a latent grid that the encoder spits out. So it's of shape this. That's the main difference between the autoencoder, variational autoencoder versus the vector quantized variational autoencoder, that in the other two we receive batch size and a single latent dim vector. Here we receive batch size, D, and this in this shape. Yes. So we're not going to call the net here. We will return the losses and other stuff here. I believe the first thing to do is to reshape our ZE. We permute it so that the D becomes the last. So we keep the batch, then H width, and that's gonna be the one. View width as -1D. But let's extract the shapes batch, the latent dim, H and W, ZE shape. And contiguous. Yes, but maybe we'll have better typings like this. Yep. So now we have a shape of BHV. I'm just gonna call this, to make life easier, as H and V, W, D. And we need to calculate the distances to all codebook vectors. And get the nearest vector. So let's say I remember that we need to use the identity was a on the power of 2 minus 2ab plus b on the power of 2. I'm not exactly sure of the tensor operations, but surely we need z2, z squared. I think I could just well, that's not any, that's a torch.tensor. So we need the length of this squared. So if I multiply, if I take it on the power of 2, that will be element wise. So I need to sum because I'm actually calculating only the d, right? Yes. For each vector of dimensionality d in the array batch HW. So I sum along dim1 and keep the dim, but why? So I just remember I need to keep the dim. It will make sense when we actually multiply this. And I would take C self.codebook. I'm going to write as much as I can from head, then fix what I don't remember from the known example, or so the B is the vector from, it's actually the whole code book. So if I just take it like it's codebook.weight, right? Because we need the matrix from the appending. So then C squared is and here, so this is this. Also need to sum along dimension B1. This is going to be K. I would like to keep now the distances will be Z2 plus C2 minus 2 times Z multiplied by C transpose, and we need to check the shapes to ensure this is fine, because Z2 now is BHVD. Okay, yep. C2 is KD. Z is BHVD, and that is DK, okay, DK. So we can definitely multiply this, because the result will be BHWK and And if I take this and move it here, then I have a BHWD, and I subtract this. That's not going to work. Only if we keep the dim here, but this is going, because I don't keep the dim. If I don't keep the dim here, this is going to be K1. So if C2 is K1, yeah, I have to peak. So, yeah, called it E here. The code quite E because of embedding. Perhaps it's better also to memorize it. And it keeps the dim. But it still becomes, still becomes 1. It just means that it doesn't remove it. So it still becomes BHW1, and this becomes K. Yeah, that was my issue with the tensor operations. And then this will make more sense because I unsqueeze it at dim 0, becomes 1K. So yeah, let's rename it here. It's better to keep conventions. So that's the unsqueeze 1K. So Z2, it's BHV1. E2, that's 1K. So I think that's fine. I can subtract it because this will broadcast to K. So this term becomes BHWK, and this will broadcast on BHW. So we take the codes now with torch.arg_min. So where the distance is minimal, on which dimension was the end result of this is of shape BHVK. Well, then on dimension 1, I guess. For all BHW, so not just for all batches, but all heights and widths. So each batch has a pixel grid, or just a grid, but let's say pixel grid. Better to call just a grid, and for each of the grid elements in the whole batch, we have calculated the distances to each vector in the codebook. So the codes we will receive for this will have a length of b times w. Without going any further, let's print the codes. There will be more code here, but say have an encoder, or just let's continue with the VQVAE, and yes, the D we need, the K we need, and we can keep the beta to ourselves. And I want to have the channels here. So the encoder channels, the insides will pass it. That's the, let's leave the dropout now. Same for the decoder, I guess. Channels, insides, the dropout we leave. Here is the vector quantizer. Insides. What? No, that's... Why? It's not the actual code. Oh, because I read the... What? Oh, yeah. Because of the copy-paste. Nice. So D is D, K is K. Yes. We have a beta, and that's all for this. Now the forward pass, this is X here. Is we have we generate a ZE using the encoder. We will get a ZQ straight through. From the quantizer. So these are the quantized vectors for each of the grid elements, the cells in that batch, and we decode them. And return that. Let's call this y hat. So y hat z e z q s t, and a little bit more later. However, 128 channels, 364, 28, 128. 16. Okay, that's, yeah, 512. Take an image from our train dataset, the train DS, pass it to VQ. And we haven't needed it so far, but it's time to declare our device CUDA, of course. So we move this to device. So move this to device. And I'm just interested in printing these. Also, let's ensure that the shapes are what I think they are. Can't multiply a sequence by none. Okay. Comma. Comma. No, not here. I guess there it is fine. Column object has no attribute unsqueeze. I just need to pick an image. That's a lot. We have 5,000 images. And well, it should be a tensor. Data trained, yes. I did not apply this transformation here. Now let's run everything again. Typo. Okay, something does work, something does not. Okay, I'll check that later. Let's check our encoder. I don't care about that, just try to run. Encoder seems to be okay. Now, can I decode ZE like in a normal autoencoder? Yeah, I guess that works. Let's return ZE and Y hat. That's a bit different than expected. So ZE should have a shape of 16 is fine. That's our D. And it's because we actually split downsample it 1, 2, 3 times. So I can pass another layer here, and that's going to affect this. Because I think we can also allow that. Because we're actually downsampling 1 time less than our channels array is. So that's 8 by 8, that's fine now. This is wrong. And it's because here we need to reverse the channels. So taking the channels, going backwards. Channel 0. this will keep the size, so I think can, yeah, it's not going to be a com transpose, that's a com. And this, it's a decoder block, it's just a typo because of the copy paste. So running everything again, and it looks fine. This is the 8x8 grids and 3 channels, so it can encode and decode nicely. Now let's take the quantizer. So we feed in ZA, ZE, and in this case we decode that. This annoys me so much, I'm going to just move it here, so I don't need to run extra code blocks. Yeah. Because now it returns 3. And let's see what the issue is. Actually, I wanted to comment out these lines. Something else is still. Okay, but it does work without the vector quantizer, right? So yeah. So the issue is there, and is this not a torch.tensor? tensor? Because it's an NN module, KD initted, and must I return something here? Because I'm then just going to return. I mean, yeah, I must, because I expect ZQST, and for now I am returning just the input. Debugging. Right, that looks fine. Let's print the rest. It's a tensor of the distances or the codes. Yeah, the codes indexes inside codes.shape has to be D by H by W. Is it not? I mean, the batch size is 1, so that's fine. The distances initially are these. Now, one technique to init the codebook is there are multiple more complicated techniques, but torch.nn. init.uniform self.codebook.weight. Now the minimum value per codebook size, make it a float, and +1 per codebook size sample from the uniform distribution. Now they are a little bit smaller distances. I'm not yet sure why we need this contiguous here. So I'll later check that. And yes, we keep the dim because we only keep the dim to this one here. And then we ask these to get that there, and this is the end shape, and these broadcast there nicely. And the codes, the shape of the codes, I think it's which one, ZE? Yeah, don't need that. So the shape of the codes is 64, which is exactly the size is, yeah, it's one-dimensional and 64. So now we need a couple more things. For example, we need ZQ straight through. Actually, we need the ZQs, not the straight through first. And we have the codes. Let's print them again to see. I mean, actually we don't need to print because those are just indexes between 0 and k-1. So the Z will be codebook, and I think you can call something like selector index. Maybe it's the, I pick it from E instead. Index select on dimension 0. Is there a better description? No. So on dimension 0 I pick the codes. Let's print these. I'm interested. But now we have so many prints. So ZQ and its shape. ZQ.shape is 64 by 16. That's our, yeah, and it's 16 because that's our latent dim, which makes sense, and it's a tensor. So the shape here is batch height width D, yep. However, we need to view it differently. So in the end we need this shape. So let's reshape it. So let's take ZQ, view it as BHWD and permute this back to batch. That's fine. We take the third, that's D. We take the first current one and the second, that's H and W. And So I believe contiguous here after the permutation, I'm not entirely sure, but contiguous after the permutation could be important, because if permutation changes up the memory alignment, we will need to pull a lot of different parts of the memory into the CUDA kernel, which is much slower. So if we just reorganize the memory into a contiguous format, then it can be a single mem copy inside the kernel. So I would say that after permute you need a contiguous call always when you're calculating with it. But to be honest, I'm going to ask the AI god ChatGPT about my theory. What? So it says, I copied this line into ChatGPT. It says, here's a cleaned up version, and it returned the same line. So what did you clean up? Because I think character by character is the same. Wow, ChatGPT, thanks for the cleanup. What is it? Is a space somewhere? Getting too many texts, and it messes up my flow. Yeah, so you can't actually even call view on this permuted tensor, because as I said, the memory will be aligned in the previous permutation. So permute doesn't actually change the data in the memory. It just changes pointers on it. So when you call contiguous, it will reorganize the underlying memory of the tensor to be in that permutation. So if you call view on the permuted tensor without calling contiguous, it might even throw an error or just silently return bad results. But that was all ChatGPT could add to my theory, so I was like correct, but not 100% covered everything. Alright, so we have the ZQs, 64 of them for a one-sized batch, but this is non-differentiable, so we cannot pass this. Backpropagation just won't work with it. So let's not print these anymore. We need this trick. because this way, if we take ZQST and say let it be equal to ZE, the output of the autoencoder, add ZQ minus ZE. So, and detach this from the computation graph. So this basically is a vector that points from ZE to ZQ. So if you add them together, you will get ZQ, but in a way that can be used for backpropagation. So we will return this. And there are two kinds of losses. There is the codebook loss and the commitment loss, which will make up the, I mean, that's the VQVAE loss, and I'm going to, yeah, add them together. Loss. So the codebook loss, what are going to be the distance as squared, and here it's gonna be ZE, ZQ, detach. I will think this through once again based on the research paper. And the research paper, because codebook loss, commitment loss. So one takes the codebook closer to the, because we fixate this loss will penalize the autoencoder output basically. So the autoencoder output will get closer and closer to ZQ. But we also want ZQ to get closer to the autoencoder, the encoder's output, but not at the same speed. So ZQ will have to move slower because we want to keep some kind of organization of the codebook, and that is what the beta is for. So in this case, this is going to be codebook loss plus self.beta times commitment loss. So the codebook vectors move 1/4 of the speed closer to the encoder output than the encoder's output moves, like basically 4 times faster, closer to the codebook. And we would definitely need to calc perplexity. I'll be honest, I recall perplexity is torch.exp, the entropy. And we need one hot encoding of something. And then average and add some epsilon. So this is just from information theory. I'm going to peek here. So one hot the codes. I did detach. Codebook loss. So it's the opposite here. Wait, let me refer to the original research paper. Neural discrete representation learning. And it's here with the stop grad. So the third term in equation 3 That's the commitment loss, this one. So beta times commitment loss. Hang on. That's fine. And in the commitment loss, you stop grad on the ZQ. Well, that's what I did. But yeah, the opposite way. So the commitment loss stops the grad on ZQ. So the commitment is for the codebook loss moves the codebook closer, obviously. This is, I mean, I would just call it like encoder loss, and it would be much clearer that it moves the encoder's output closer. But they call it commitment loss in the paper, so we have to deal with that. That's the terminology. But so commitment loss is the encoder loss. And getting back to perplexity calculation. One hot the codes. Okay. We will have one hot vectors for each code. We calculate the mean on dimension 0. Why? I'm asking. That gives the average probabilities. Let's think this through. And entropy is by the book. Not that I remember it from university. It was long, long ago. So entropy minus P by P log sum. So we one hot the codes. That is self.k. Yeah, convert it to float, of course, but because we will take the mean, let's output one hot. The one hot point shape will be, well, it's going to be a matrix on the batch, and oh wow. What's wrong? I'm returning more, but I'm also going to return perplexity, which is the measure of how much the codebook is utilized. So these come here, and ZE, ZQ, ST, and it returns 5 values in total. Perplexity, entropy, exponentiated, entropy, well, I'm going backwards, but so take average probs will be one hot, mean, dimension 0, average probs dot mean you divide it by this, and here I add the epsilon. then normalize it, and then just calculate the entropy. So this is a normalization, and this is very important because when I didn't do it, it was yielding unreal perplexity numbers. So 1 hot plus some epsilon, really small number, and just with the sum we normalize. It's going to be minus average props time average props dot log dot sum. So the Shannon entropy formula for a discrete probability distribution P is HP minus, yeah, that's literally the textbook Shannon entropy formula here. Summarize the probabilities with the log of the probabilities. Too many values to unpack. Yeah, probably. Unpack all of this. And now we have 64, 515, that is the codebook size. Codebooks is in this shape. I mean, the codes. The codes are B times H times W, and of course we create a matrix of that, self.k. So maybe if I just say 5 codes, then we can see it much better here. So there are 5 codes. This is the one hot encoding of the codes. So this is a statistic that for each returned code for each distance, so for each ZE, which code is the closest in the code book, it will mark it with 1. And of course multiple ones will be present probably in one column. So if I mean it on dimension 0, if I average it, let's print that out. With the small epsilon I know, but so we get the means for all, which means how much each code is used, kind of. We normalize it. We absolutely need to normalize it because the Shannon entropy is calculating with probabilities defined between 0 and 1. Also that, I mean, this will also stay between 0 and 1, but I think these are just really small numbers. Anyway, if you normalize it, compare the values. Are they the same? Looks like they are the same. That's just the epsilon. I mean, those are just numbers, right? So what are we even summing here? If it's just a number, the sum will be itself. I mean, you can call the sum on it, I guess, but it will just return, but it doesn't return. What does it return? It sums up to be 1. I mean, it probably average props the shape is this, and if I call just the sum, it won't be a column-wise sum, it will just sum everything. So let's just try and not divide by the sum. That will just make life easier. So we one-hot encode the codes to be able to arrive at this usage array, basically, or usage matrix. And if we calculate the mean on dimension 0, that means we will have a probability of that code's usage plus a little epsilon. That's a pretty neat formula, by the way. Really cool. Okay, I think I get it now. So, once again, the whole vector quantization thing, from beginning to end, encoder spits out basically a small grid of latent vectors. We need to reshape it because that is just how the images are arranged in Torch Vision, or that's the standard, like the channels are here. So that's because of that, basically, because the channels become the latent dim, we just need to move it to the last element, so we will end up with batch times h times w number of latent vectors. This is just a shorthand for the codebook white matrix. So in the codebook white matrix, each row is a discrete, it's a separate vector in the codebook in that latent dimension. We calculate the distances to all codebook vectors from all of these BH, this number of vectors. So we use this identity because it's easier to calculate on the GPU, I guess, than algorithmically finding it. So we can easily take the Z, this array of Z's, square them, sum along dimension 1, this, and this will return, we keep the dim, so this doesn't go away. And that will be the length squared, yes, of each of those vectors. We take the length squared of each of the codebook vectors. That's also on the same sum on dimension 1, so this, same way. However, we need this in this shape for this calculation, so it broadcasts nicely. And let's start from this. That's this many times k, so that's because the distances, we will have k number of distances. Actually, we will have the distances. I should create a new variable for this. It's hard to say. So BHW number of are the number of the incoming latent vectors, and we calculate for each the distances to all codebook vectors. So that's why it's here. Each output of the encoder gets the distances to all codebook vectors. And Z2 is obviously in this shape because there are BHW number of Zs. And obviously E2 is in this shape because there are K number of codebook vectors. So now we just find the codes, which are the indexes for the closest dimensions along dimension 1. So this is the codes for each incoming ZE, basically. Not ZE, but this vector for all of these. So the closest codes for all of that. And the ZQs will be the index select on dimension 0, because we are picking the nth d-dimensional vector from the codebook. And we just view it, we split it up again because we will need that format, permute back and make it contiguous. we use a ZQ straight through because we need this for to be differentiable during backpropagation, and we wouldn't be able to use this ZQ index select, and argmin is not differentiable. The codebook loss measures how much the codebook, or maybe it's better to remember like that the codebook loss pulls the codebook, so the ZQs closer to the ZEs, and the commitment loss is the opposite way, it pulls the ZEs closer to the codebook. And the total vector quantization loss is codebook loss times the commitment loss. Is this for sure? Because this will, so the codebook loss, so this will move the codebooks vectors closer 4 times faster to, so actually here the codebook is moving faster than the ZEs, which kind of makes sense because you want to train the codebook to adapt to the learned features and not the learned features to move harder to the codebook, because we want to keep the structure much more than force it to be in that codebook or where the codebook is. And we calculate perplexity by generating one-hot vectors from the indexes, the codes. This way, if we take the mean, so yeah, if we take the mean along dimension 1, we get the probabilities, average probabilities for each code, because say a code is used 50% of the time in this batch, or actually in this, then 50% of this k will be, no, 50% of this, so b times h times 2, this will be the number of ones in a column. And if you take the mean of, say for example 100 zeros and 100 ones, that will be 0.5, so that's a 50% probability. Now we use the Shannon entropy formula from the textbook, which is just basically p times the log of p summarized and with a minus, and the perplexity is just this term exponentiated. Cool. Now this way we have our vector quantized variation autoencoder ready for training. Okay, let's write the training code then. Epochs, I like it to be 100 for small examples like this. Learning rate. I really don't want to write everything again, but I will. So now using torch.inference mode, which is newer, and they say it's better than torch.nograd. It's even faster, so let's write the eval model function before we write anything else. And for x in data test, we need the image column. That's the test data loader. And just to be safe, let's switch the model to eval. And since this was just some test code, I want to redeclare it here. So the input size, alright, that's fine. The latent dim can be small, but the K needs to be around 500. And we move it to the device. Now let's also move this to the device. Yep. And let's also define, we have an optimization torch.optim did be Adam. That's the model.parameters. So let's print them here. Num params times a million, I mean divide by a million, and 2 digits precision. Now we have our Adam optimization and optimizer. The learning rate is, yeah, I'm going to set the learn and everything else here except for the epochs, because if I want to retrain, then I will just use this code block. I mean, if I want to train further, I will use this code block, and this will keep the model wise. Now I want to use the grad scaler, and I need to use the grad scaler because if I use autocast and it converts the F32s into F16s, half precision can't represent the gradients as well as F32s, so it could lead to issues with backpropagation if they are rounded down to 0. So the grad scaler will just scale up the gradients and then scale them back when inference happens, so they don't get rounded to 0. Yeah, so there's the optimizer. Yeah, optimizer. Now the grad scaler. Yeah, the device is CUDA. Init scale enabled. Yeah, we don't need anything from there. And it's a lot that this returns. And I want to keep track of the losses and the perp. Let's just say that, what if I made a single tensor for all of this? And here, mean square, okay, that's fine. Yeah, just call model, of course, with X. It's already on the device. Cool. There's also a recon loss because that's not the total loss. So the recon loss is mean square between y hat and x. So the final loss is the reconstruction loss plus the VQ loss. And I'm going to push the final loss to losses, and perps will take the perplexity. Then average loss will be torch dot. Loss is a single number, so I can create a tensor from it. I mean, losses is an array, so I can take the mean like this easily, and the average perp same way. I'm not printing anything, just returning average loss, average perp. Yes. And I'm evaluating the model without any training at first. So initial average, let's call it test loss, because we call it's the test data set. So that's average init loss, init perp, so test loss, init loss 4. It's going to be, yeah, that's gonna be fine, that precision. So perplexity init perp, we don't need that much because perplexity moves, it's almost basically the number of codes that is used in the code book. So it should be around 80-90% of the total codebook size. So we don't need much precision here. It's going to be a large number. This doesn't work because I need to sum this up. 1 million parameters right now. It's not a big model. So for epoch in range 1, epochs plus 1. Can copy this code almost, except train. Except obviously need the loss dot backward here, but first we need to use the scalar to use the scale outputs. I haven't really used the scalar so many times, only once, so but let's just do the original without the scalar. Here we don't need to use the scalar because it's in inference mode, so I can do torch.autocast. Like this. Same way here. But scalar. That goes for each batch. So then I would say optim 0 grad, set to none, true. I would say loss dot backward and optim dot step. but scalar.step optim and scalar.scale outputs to scale. That's, I'm not sure we need this. Definitely need the update and one more method. Let me peek, it's not really it's an optimization. So I have a grad scaler here. We scale the loss and then call backwards. Step the optimizer and update the scaler. So basically this is just a wrapper, and I can call the zero grad happens here. Well, I will zero it here. So instead of loss.backward, I scale, it's just 3 lines together. Scalar dot scale the loss dot backward. Scalar dot step instead of optimizer step, and scalar dot update. 3 lines when using autocast, and autocast this should be inside autocast, right? Because it doesn't make sense. Only makes sense if it's inside the autocast, no? Okay, so it should be outside. And only the model's forward pass and the loss should be inside. The loss should be calculated inside the autocast. So the gradients, even though, so here we create, and this definitely shouldn't be here. So let's, this is gonna break so bad. Yeah. Anyway, putting it here. Okay, I'm just gonna stick with remembering this because it doesn't really make so much sense how it exactly stores, and ChatGPT just can't explain. I would have to dig some documentation. I'm not so really interested about right now. More interested about the model itself and how it trains and converges. So basically autocast on the forward pass, there will be some 16-bit floating point numbers generated, and this scales back the loss. So when the backward pass happens and the gradients are still in float 16, they don't get this gradient underflow, so they don't get rounded to 0, and that's it basically. We 0 grad here, and we could 0 grad here as well. So for each epoch, if EP mod 10 equals 0, 5, or EP equals epochs, print epoch EP, train loss will be average loss. We evaluate the model. Test. Let's just break this line. So train loss. Shorten some stuff, so that becomes dr loss, dr perp. That's the average perp. Precision was maybe just 1, yes. What else do we have? I mean, we could print the recon loss and the VQ loss. Not now. So print the test loss. Test. I mean, the test perplexity doesn't. Does it even make sense? Should I? Evaluation loss, evaluation perplexity. misses the device type. CUDA. Same here. I forgot to detach the losses. So loss dot detach. Same for perplexity. Don't need here because it's inference mode. Meanwhile, I'm going to use my utility functions for just showing images and GIFs. So show img, show img, squeeze it at 0. That's y hat. So perplexity looks okay because it's growing. I mean, I could train this for a much longer time because around 66 codes are used from more than 500. So this won't give any good results. But just using 66 codes and already receiving back pretty good quality. Let's train this further. How much? It was 2 minutes to train this for 100 epochs, only 1 million parameters. So I have maybe 6 more minutes, and by then, yeah, I should print the learning rate as well. If we start to change the no, I will not add a learning rate scheduler only when I see that it doesn't train anymore or converge, lower the loss in a meaningful way. Keep it simple. So we are training further. This is epoch 120. More and more codes are used from the codebook. And I would be fine with 450 codes, so we have a long way from 83. So this is just going to be this boring part of the live. Pretty good utilization, almost 200. Oh, come on. Well, the last one will be printed here anyway, so yeah. So it trains very fast because I guess, well, mostly because we are just dealing with discrete vectors for fixed size. This is not a big network, only 1 million parameters. Well, to be fair, it appears that the epochs are running faster, but total time-wise, it's not faster. However, I would expect much better results. And when this training finishes, this will mean that we have this faces dataset, and we have exactly 512 tokens from this dataset. So these are discrete tokens, just like ChatGPT's tokens, but for images. And I'm going to implement this once again, I think, or maybe take this live, cut it, and that will be the video. Now I have to explain more in a video, but also what I wanted to try is add the skip connections. I definitely want to add skip connections. Connect encoder layer EI to decoder layer DI at the same spatial resolution. I'm not sure I want to. I mean, for maybe. I I definitely want residual blocks in the encoder and in the decoder separately. I'm not sure I want to connect the encoder and the decoder besides the latent space. And yeah, an interesting research article I read is that it's, as I recall, it splits up the image into areas, and or it splits up the latent vector into parts and uses multiple code books, so multiple quantizers, and then it concatenates it back again, and that gets decoded. I don't know for why, but it sounds interesting, and there's definitely a good reason. Not exactly how she looks. Time in harmony. Yeah. We could train for 100 more epochs, but I don't expect. So I want to compare this image with the one if I add residual connections or blocks. But I cannot really add the input because this downsamples. So I would need layers that don't downsample. Ah, 100 more. I can add skip connections if I use a kernel size 1 with a stride of 2 that I use. That will downsample, so it's a skip connection, but I'm not taking the raw input. Now in this way, the enc block We need to make it a class. But let's just define our training finish. $430. Maybe here I could start decreasing the learning rate. Let's try that just manually for 50 epochs. Or like 5E, 5. I think this is the closest I will get with this architecture. I mean, for a 1 million model, it's really cool, and the latent dim is just 3. So we have 512 three-dimensional. It's still it appears it's getting better. I promise this is the last time I'm training it further. Perplexity just stays around 430, it's not going above. Now it's climbing up a hill. Okay, 0059, same from the evaluation, that's perfect. And I didn't make any mistakes, so the test data set is the test data set. I'm not running it accidentally on the train data set now. So that's what we get without skip connections. I'm going to make a screenshot. VQVAE base, no skip. And take 2, this should be called, I'm not gonna rename it, it loses the state. So this will be a working base. And this one now, let's change the enc and the decoder block to be actual modules. So the encoder block becomes a residual down sample block. We have this as a sequential. We have this. No, we don't need that. And the skip connection is also a sequential. And then conv2d. In channels, out channels, kernel size 1, stride 2 to downsample, padding we don't need. And group norm it the same way. Groups out channel. Now here we can do self.skipx plus self.netx. And yeah, need to modify this. So that's gonna be, I don't need to do this per layer anymore. I can just do residual downsample, downsample block, CNC out like this. Now we have residual upsampling blocks with this. And we need to upsample conv transpose 2D, that's done. So I'm not just using a conv transpose there. I mean, I could. Let's try that. Or I could use upsample and then a convolution, because that doesn't insert zeros like conv transpose 2D. So maybe that's better here, to scale up the image to size none. So I can just use the scale factor, which is 2. Explicitly defined, we are using nearest. Perform a convolution to get those number of channels and normalize. But of course the last layer will be anyway just this. And the same way I will just use the residual upsample block. Drop out. Okay, let's use it. Let's train it for 500 epochs. Too much waiting. Let's train 400 and see. Did I not reset the model? Yeah, I did not reset the model. So now we have a bit more parameters. Can we get the loss further down? Is one question. Okay, we can train like 300 more times. Meanwhile, Genie's video tokenizer uses the same VQVAE, but with a spatial temporal transformer. So next I want to do that. So instead of a convolutional neural net as here with residual blocks, we are going to use an ST transformer based one. And the ST transformer can capture feature dependencies on the frames themselves and between the frames as well. This is really interesting because I guess so the ST transformer captures these spatiotemporal dependencies on the frames, and then you arrive with a latent vector quantized in this latent space. So that latent vector actually, it not only encodes the image features, or in case audio, the temporal features. That one vector is actually it's like a feature vector of an animation, or like it has motion in it, basically. It's kind of like 3D, like a feature of something animated. So it's an animated feature of a continuous, discrete but flowing video. That's really cool. So Genie's video tokenizer uses 1024 unique codes with an embedding dimensionality of only 32 and a patch size of 4 pixels per token. Four pixels per token. So actually I could lower here from 8 by 8 to 2 by 2 and probably we would get better reconstruction. And we use group normalization heavily, so I could add even more layers safely to this network. It won't get deep too much. The loss combines the usual blah blah blah. Apparently the encoder of Genie uses 12 transformer layers with 8 heads, while the decoder is heavier with 20 layers. Are you sure, ChatGPT? Well, it just extracted the info from the research paper. So in order to create that video tokenizer and basically the encoder and the decoder, let's just forget about the action model of Genie. The next step is to implement an ST transformer. I might just skip the video about normal transformers entirely. For me, it would also be interesting to take like n frames, n previous frames, and apply 3D convolution on it, because with that, like it's hierarchical in the temporal dimension as well. If you build it like that, so it can extract temporal dependencies the same way as it can extract spatial dependencies, and then you don't need the convnet. But I guess people tried this already and it didn't work out that good. So Conv3D has fixed temporal context size, e.g. kernel size of 5 sees only 5 frames. I mean, yes, but on the deeper layers, still far away features can be connected. Okay. Well, the loss is still pretty high. Let's train this a bit more on 5E5. But I don't expect anything much better than previously. If I should scale down the image, I will try to scale it down to 2x2 patches, because I mean the training loss is still, it's not really good. It's even worse than before. Now we have skip connections. So for this network with this configuration, even with skip connections, this is the maximum. Same perplexity, but higher training loss. So we're at 8x8. So more. And yeah, let's just try downsampling even more. And we only change one variable in the model, so we will know what affected it and how. Okay, let's see this now. That's kind of the same. Okay, save VQVAE, skip cons. And now we have a much deeper model. Try, keep it 3. Yeah, because now shouldn't be, yeah, it's gonna work like this. Pairwise it downsamples, so it downsamples length channels -1. No, Nah, the learning rate isn't. Learning rate should be the initial. I could already split this model with FSDP and it would train faster. Not in a notebook, however. I'm not even sure if I could do that. But soon we will work in normal Python files. So Genie uses 32-dimensional embeddings. What? Per size 4, but so it means 2 by 2 pixels. But here it down samples. So it's 1, 2, 3, 4, 5, 6, 7. So 6 times. That's gonna be 4 by 4 because 64, 32, 16, 8, 4 by 4, 2 by 2. Yeah, it needs to be 2 by 2. Okay, 100 more. Yeah, so the video for the ST transformer, there is an additional dimension, T, of course, because we're not dealing with images, or we are dealing with batches of D number of H by W times channels frames. So if this is training this slow, I will have to leave it to train for a day at least. Is there an NN dot multi-head attention? Wow. Yeah, I'm not going to use this. Definitely. So the ST block uses two of these, of course, one for spatial, one for temporal. And MLP. That's still pretty high. Let's train for around 500. That's how long I trained the previous ones. So the idea is to convolve the frames, arrive in a latent representation for each frame, each patch will have its own representation. So basically like here, but for each frame in a batch. So we keep the patches, and before applying the vector quantization, we run ST transformer blocks. The ST transformer, yeah. The ST transformer receives the input as B, T, N, D, applies attention spatially, then permutes the dimensions, applies temporal attention, then uses an MLP head, and then it gets quantized. So basically discrete ST features are generated, and these quantized tokens feed into the ST transformer decoder, reconstructing the original frames, but so transformer block by itself has residuals. Of course, don't need to explicitly implement it like here. But we definitely need to create these patch embeddings. So convolution, maybe with residual, maybe without. Then we have these small patches and D number of channels, and D is the embedding dimension. That is fed into some ST transformer blocks after each other. Then we quantize it. Then I guess again feed it into even longer sequence of ST transformer blocks, and then a convolutional well, basically the end of it is a decoder like here. So we can almost keep this. Maybe totally keep this and just add the ST transformer. So yes, but we need to extend this with another dimension, T, so it can take multiple frames. Also, we need a data set from Hugging Face. Video data set. Or I will need to pull lots of videos from YouTube, scale them down, or play Prince of Persia for a very long while, and then the model will only be able to generate Prince of Persia, nothing else. Anyway, the goal here is to create such a model architecture that is able to, that you can train on a large data set as well. So you just need to scale your hardware. Obviously, having a larger data set and a larger model comes with its own challenges. This is still worse. But the perplexity is just 104. So maybe we just need to train it for much longer. But I give it 30 more minutes and then I have to head off. Only 302 is used from the 500. I think I should bump this up, but if I bump this up, whoa, that's a dude, bro. That's not even her. That's someone else. Jeepers. Okay. Let's. How big is the model? Not much bigger. That's a bigger model. So we have 32 latent D now, and 256 for the number of channels in the last 3 layers, or the deepest 3 layers. And the patches are 2 by 2 pixels. The bottleneck here is if we have 2 by 2 pixels, we only have 256. Channels with 27 numbers, because cube of 3. Okay. Also, Genie, actually, they don't scale it down to 2 by 2. When they say patch size of 4, they mean 4 by 4, so I'm downscaling it way too much. That could be one reason it doesn't converge. So let's just try 350 now. Latent dim. Latent dim, latent dim. Okay. Huh. 32 dimensions, okay. So, hang on, did I? Yeah, so this is 2, 4, 6, clear down 5 times, yes. So now maybe Genie doesn't use a deep convolutional network, it only uses a single layer, but of course it's not really detailed. I should do some GitHub research to find anything more specific about how Genie encodes stuff. Now I want to save a checkpoint, I guess. Torch dot save model dot state dict. Let me look up. Yeah. Yeah. Two checkpoints. VQVAE. PNG, PTH. Maybe I will. I should save the full model. 32 ST transformer blocks after each other in total in the encoder and the decoder. And where's the Genie paper? Genie paper, Genie paper, Genie paper. Nope. So I don't need this. The dynamics model is decoder only mask it. So I need the SD transformer implementation. Get it to train somehow. Then the dynamics model is a mask kit, so you'll need to implement mask kit. And the latent action model, not now. That's the smallest part of it. And they trained it on 30,000 hours of videos. Definitely can't do that. So I'm gonna have to find a fun way. For example, they only worked on 96 by 96 images, 11 billion parameter. Where do they say? Nope. Run it a bit more. Perplexity is just 10%, so maybe this trains slower, but a more stable way. That's not guaranteed though. $200,000 hours actually. Genie is trained from a large dataset of over 200,000 hours of publicly available internet gaming videos. Do they actually say about the resolution anything? Okay, the results show that our so only the platformer games part is 30,000 hours. What if I went back to like Commodore 64 style games? Even the resolution there is too big for anything. Achievable at home or without sufficient funds, as I'm not connected in any way to any big tech company to have such resources. What's the smallest resolution ever on any machine where people played games? Or if not games, then I could model something else, but need to have sufficient training data for that thing. I could model the growth of a graph, growth of fungi, for example, like the slime mold, and the output would be a graph encoded into frames, but I don't have training data, thousands of hours or even 100 hours of slime mold growing and then converted into graph data. I know this part of the life has become pretty boring, but it's just how it is with training a network. It's not the implementation itself that takes long. So for a home implementation of Genie, I could maybe work with 32 by 32 and oop. And how many frames? So the context size an encoder takes as input all previous frames as well as the next frame and out the corresponding set of continuous okay, that's the latent action model. Continuous latent actions. Decoder then takes all previous frames, latent actions as input, predicts the next frame. So VQVAE is great here because you can just say the codebook size is 8. Then between each frames you have a maximum of 8 actions. But you need to also predict the next frame pixels. Yeah, it just takes t frames. And what's the sample number for t? So the video tokenizer here just tokenizer. So it takes in t frames and outputs the same t frames, at least at this part. Because then it will need to infer the next frame. So are we reconstructing same frames, and where are we predicting the next frame? So it predicts future masked video tokens. Yeah, I need to do research into what this exactly does and transform. So the dynamics model predicts the next frame tokens. Yeah. cross entropy loss between predicted tokens, ground truth tokens. Train time, we randomly mask the input tokens according to the Bernoulli distribution, masking rate sampled uniformly between. Okay, why the model is train time, we randomly mask the input tokens. Concat the action, but they add yeah, because yeah, anyway. Okay, but that's just T frames. So if I want to switch it and generate more frames, so the dynamics model generates the next frame, next latent frame from the previous, and the actions, that's cool. And the video, so they train this. I guess they feed in T number of frames and the decoder just reconstructs the same. And when that's trained, the weights are frozen. So it already has a can already encode into latent pretty great. So it works awesomely with its ST transformers and whatever. And then they train the dynamics model with the tokenizer, encoder and decoder weights frozen. It's just my assumption. So that even if T equals 1 and there's one frame and one action initially, the dynamics model iterative generation up till T. Yes, but I want indefinite. So what I would need is to pass a single Z to the decoder that the dynamics model generates based on history. And it should be able to output single frames in an autoregressive fashion as well. Oh, come on. Just 50 more. Give me 50 more. I mean, it's converging nicely, it just takes a long while. I should have probably just downscaled the images to 64 by 64. No, I don't have that data set. I should create that data set, but perplexity is growing steadily. I'm not sure now. Train loss isn't so good at the moment. It doesn't, you're right, it doesn't exist. Now it does. Okay, save the model. Yeah. It's something, definitely, but with this low perplexity, did it stop converging or? Because a patch size of 4 in this case, because this network is a deep convolutional network, might not work. So Deepmind says they have 24 by 24 grid of patches. At least that's what ChatGPT hallucinated. Latent video tokenizer training, okay. 64 TPUE, okay. Num layers 12, D model. Yes, num heads 8, is 64, 20 code book. Batch size is 4. Latent dim 32. But here the encoder is basically a sequence of transformers, and maybe there's only one layer of convolution. $300,000 steps using ADAMW with cosine decay. Using the hyperparameters in table 8, max learning rate 3, mean learning. Why are you, what? Beta 09, beta 209, why did they say? Okay. Ah, it's for the weight. It's a weight decay, okay. Not for the learning rate. 10,000 warm-up steps. So I'm just training for a few hundred steps. Yeah, no wonder. What if I train with ADAMW? I'm not gonna. Okay, time's up. Thanks for watching the live, and see you next time where I'll fiddle with the ST transformers. Maybe I will leave this to train for the night. Maybe not, because I don't really. It's converging. But I won't be home at tonight, so I don't want to leave the machine. Okay, anyway, good.